Hello, my name is Ryan Grainger, and I'm excited to present PaCa-ViT, Learning Patch to Cluster Attention in Vision Transformers. Transformers have been the default choice for state-of-the-art AI, mostly due to their simple architectural design, leading to general and powerful models. Vision Transformers utilize a patched-based tokenizer, which has a semantic gap with its natural language processing counterpart, the textual tokenizer. Patch-to-patch attention also suffers from quadratic complexity and doesn't account for redundancy of information within the image. It's also non-trivial to explain the learned patch-to-patch attention. We aim to answer these three problems by utilizing clustering. In our work, we study how to do the clustering, where to do the clustering, can we leverage an external teacher network to do the clustering, and what if we already know the number of clusters we're interested in, like we are in semantic segmentation. Efficiency is incredibly important for many applications, and to address the efficiency problem, some transformer models leverage inductive bias back into the network. You can do this by constraining the attention to a local size window or by performing spatial downsampling. Additionally, we can exploit low-rank projections to form coarser-grained tokens. Our model facilitates learning expressive and meaningful visual tokens beyond that of the patches found in vanilla ViT models, while simultaneously addressing the quadratic complexity and enabling a forward explainer. Our semantic segmentation head is lightweight and more expressive than the widely used UpperNet and semantic feature pyramid networks. In the vanilla patch-to-patch attention, the input is projected to queries, keys, and values using a linear projection. Queries and keys are matrix multiplied together, introducing quadratic complexity. In our proposed patch-to-cluster attention, the keys and values are linearly projected utilizing a latent space vector, Z, which is generated from our clustering assignment, where the clustering assignment is generated from the input. When computing C, our clustering assignment, we have three basic choices. We can do a linear projection followed by a softmax, an MLP followed by a softmax, or we can inject inductive bias and use a convolution. We note that the first two are domain agnostic, while the third is domain specific. Next, we investigate where best to perform the clustering. In on-site blockwise clustering, each block performs its own clustering assignment. However, in on-site stage-wise clustering, only the first block in a stage computes the clustering assignment, where the rest of the blocks in the stage use the original clustering assignment. Here we give an overview of our architectural model, where we have 4 stages. In each stage, we use stage-wise on-site clustering. Our stem and transitions are a convolution followed by layer norm. And our feed-forward network is a linear expansion, depthwise con activation, followed by a linear contraction, as well as some additional architectural choices. We also explore how to use an external teacher network. Here, the external teacher network performs the clustering for us and incorporates a top-to-bottom, bottom-to-top information flow for these clusters. Here's some additional information on how we create the teacher network, as well as some additional architectural design choices. We also ask, can we use this style of external teacher network to distill information from large foundation models? Some additional ways to consider thinking of the PaCa module is that computing the latent space vector Z can be thought of as a learnable depthwise global weighted pooling of the input, where the learned weights are our cluster assignment. Additionally, you can think of it as a dynamic MLP mixer with data-driven weight parameters of the cluster assignment. The latent space vector Z shares a similar spirit to class tokens or task prompts used in vanilla ViT models. And lastly, the computing of ZM sub C can be thought of as performing cross-covariance attention. Here, we ask the question, what if we already know the number of clusters a priori, like we do for image semantic segmentation? In this case, we use a singular single-head PaCa module to generate the segmentation results. In our experiments, we focus mainly on these three models, which utilize stage-wise convolutions. But for comparison, we also incorporate stage-wise MLP versions, as well as 2 additional external teachers. Here, we show the results on image classification for ImageNet 1000, where our base model outperforms Sween Small and Sween Base, as well as PaCa-ViT V2, B3, and B5. We do note that our clustering overhead makes our PaCa module slightly more expensive than PaCa-ViT, but only for image classification, as the overhead will be paid off as you move to object detection and semantic segmentation. Here we display our results for object detection in MS COCO, where our model achieves a mean average precision of 43.3. Here we show the results of our image semantic segmentation, where we display the large performance boost we gain by utilizing our segmentation head versus UpperNet. Here we perform an ablation study on the number of clusters, particularly on the PaCa small model. Lastly, we study the results of the interpretability of the PaCa module. Utilizing the heat maps generated by a clustering assignment, we can generate masks. And for each masked image, we create a positive and a negative group. The positive group, in which the masked image can still predict the ground truth, and the negative group in which it was wrong. Noting that the positive group means that the masked portion contained enough semantic information to correctly predict the image. Here are some examples from the positive group, noting that some of these masks have a significantly higher prediction than the original ground truth. Here are some results from the negative group, noting that most of these focus on background information. In summary, we have additionally provided another way to perform attention that maintains both explainability and efficiency. We would like to thank these people for their support, as well as you for your attention. Thank you.